So here's something you probably haven't thought about today, even though you've relied on it 100 times without noticing. Measurement. The simple act of putting a number on something. You glanced at a clock this morning and knew what time it was. You stepped on a scale, or checked the temperature, or poured a cup of coffee, and knew roughly how much was in it. You drove somewhere, and your speedometer told you how fast you were going. You bought something, and it was priced by weight or volume or length. A pound of cheese, a gallon of gas, a foot of cable. You bought something, and it was priced by weight or volume or length. A pound of cheese, a gallon of gas, a foot of cable. Maybe you checked the weather app and saw that tomorrow would be 72 degrees, or 22 degrees, depending on where you live and which system you grew up with. And none of that felt remarkable. None of it felt like a miracle. But here's the thing. Every single one of those measurements rests on top of a vast, invisible, extraordinarily sophisticated infrastructure of human agreement, scientific discovery, political argument, and sheer, stubborn effort that stretches back thousands of years. The fact that your kilogram is the same as my kilogram, that your second lasts the same duration as a second in Tokyo or Nairobi, or a satellite orbiting 300 miles above your head, that's not obvious. That's not natural. That's the result of one of the most ambitious and underappreciated projects in the entire history of civilization. And that's what we're going to talk about tonight. Measurement. The whole long, strange, surprisingly dramatic story of how humans figured out how to agree on what things mean when they say a foot, a pound, a degree, a second. We're going to start way back at the beginning, in the ancient world, and we're going to take our time walking through it all. The breakthroughs, the arguments, the spectacular failures, the obsessive personalities who devoted their lives to getting one number just a little bit more precise. And if you drift off somewhere along the way, that's absolutely fine. You'll pick up the thread again. Some of this stuff is the kind of thing that lands better when you're relaxed anyway, when your mind is loose and wandering, and not trying too hard to grab onto every detail. Let's start with something so basic it almost seems silly to mention. How do you measure something? Like, the very first time anyone ever wanted to know how long a piece of wood was, or how far it was to the next village, or how much grain would fit in a jar. What did they do? They used the only measuring instruments they had, their bodies, an arm, a hand, a foot, a stride. This is where our oldest units of measurement come from, and you can still hear the echoes of it in the language we use today. A foot is called a foot because it was, originally, the length of a human foot. An inch comes from the Latin word uncia, meaning a 12th part, a 12th of a foot. A yard is roughly the distance from the tip of your nose to the end of your outstretched arm. A fathom, used for measuring water depth, is the span of both arms stretched wide, fingertip to fingertip. And the most famous ancient unit of all is the cubit, the Egyptian royal cubit. This was the distance from your elbow to the tip of your middle finger, roughly 18 inches or about 45 centimeters. And the Egyptians took it very, very seriously. They had a master cubit, a reference standard carved from black granite, and the workers who built the pyramids had their own working cubits, wooden rulers calibrated against the master. If your working cubit didn't match the master, you were in serious trouble. Some historians believe the penalty was death, though that might be a bit of dramatic embellishment. But the point stands. Even 5,000 years ago, people understood that if your measurements aren't consistent, your buildings fall down. The Great Pyramid of Giza, built around 2560 BCE, has a base that's about 756 feet on each side, and the four sides differ from each other by less than 2 inches. That's astonishing precision for a civilization working without anything we'd recognize as modern engineering tools, and it only happened because they had a reliable, standardized unit of length and they enforced it rigorously. Now, the Egyptians weren't alone in having sophisticated measurement systems. The Mesopotamians, in what's now Iraq, had their own units. The cubit there was a different length than the Egyptian one, of course, because that's how these things go. The Romans had a whole system based on the foot, the pes, about 29.6 centimeters, and they subdivided it into 12 unciae, which gives us our word inch. And they were remarkably consistent about it, probably because the Roman military needed standardized measurements for building roads and fortifications across a sprawling empire. When you're building a road from Rome to what's now London, you need everyone along the way to agree on how wide it should be. Archaeologists have found Roman rulers in excavations across Europe, and they're strikingly consistent. The Roman foot varied by only a few millimeters across different examples, which is impressive for a civilization without precision manufacturing. But here's where it gets interesting, and a little bit messy. The cubit worked beautifully in Egypt, where you had a centralized authority, the pharaoh, who could decree that everyone would use the same standard. But what about places without that kind of centralized power? What happens when every town, every market, every guild is left to figure out its own measurements? Chaos. That's what happens. And for most of human history, that's exactly what people lived with. Think about medieval Europe. By the Middle Ages, there were literally hundreds of different units of measurement in use across the continent, and many of them shared the same name but meant completely different things, depending on where you were. A foot in Paris was not the same length as a foot in London, which was different from a foot in Rome, which was different from a foot in Zurich. A pound of goods in one town might be 10% heavier or lighter than a pound in the next town 20 miles away. A gallon in England held a different volume than a gallon in Scotland. The French alone had over 800 different units of measurement in use before the Revolution. 800. Imagine trying to run a business, or collect taxes, or build anything, when you can't even agree on how long a foot is. And the confusion wasn't limited to Europe. In China, the qi, a unit of length, changed its value dramatically over the centuries. A qi during the Shang dynasty was roughly 16 centimeters, while by the Ming dynasty, it had grown to over 30. In Japan, different trades used different versions of the shaku, a unit of length. Carpenters used one length, fabric merchants used another, and surveyors used a third. Even within a single country, within a single city sometimes, different guilds might use different measures for the same type of quantity. And it wasn't just inconvenient, it was a source of enormous injustice, because the people who controlled the local standards of measurement were usually the local lords, the merchants, the guild masters. And if you controlled the measuring tools, you could cheat. You could use a larger bushel when buying grain from farmers and a smaller bushel when selling it. You could use a shorter yard when selling cloth. The common people knew this was happening, and they resented it deeply. Complaints about unfair weights and measures show up in petitions and grievances throughout European history. It's there in the Magna Carta in 1215, which includes a clause demanding that there shall be one measure of wine, and one of ale, and one of corn, throughout the whole realm. It's there in the Cahiers de Doléances, the lists of grievances that ordinary French people submitted before the Revolution in 1789. Over and over, people asked for fair, uniform, honest measures. Measurement wasn't just a technical problem. It was a political one, a moral one, even. It was about power and fairness and trust. Who decides what a pound is? Who decides how long a foot is? These questions sound trivial, but they determined who got cheated and who didn't, who could trade honestly, and who was forced to accept whatever the local lord's rigged scales said. In a very real sense, the fight for honest measurement was a fight for justice. And it's no coincidence that the most comprehensive reform of measurement in history came out of the French Revolution, a movement that was, at its heart, about dismantling the arbitrary power of elites and replacing it with something rational, something universal, something fair. Now, various rulers over the centuries tried to impose some order on this mess. Charlemagne attempted to standardize weights and measures across his empire around 800 CE. English kings from Henry I onward made repeated efforts. There's a charming story, probably apocryphal, that Henry I decreed the yard to be the distance from the tip of his royal nose to the end of his outstretched thumb. Edward I tried again in the 1300s. Elizabeth I tried in the 1500s. None of it really stuck. The problem was enforcement. You could decree whatever you liked from your capital, but out in the provinces, in the small towns and rural markets, people kept using whatever measures they were used to. Old habits die hard, especially when the people who benefit from the confusion are the same people with local power. So for centuries, the world muddled along with this patchwork of inconsistent, overlapping, often deliberately deceptive measurement systems. And if you're thinking, well, that's a problem for medieval people, it doesn't affect us. Think again. The United States, right now, today, is one of only 3 countries in the world that hasn't officially adopted the metric system. The other 2 are Myanmar and Liberia. The US still uses inches, feet, yards, miles, ounces, pounds, gallons, a system that is essentially a fossilized remnant of the medieval English hodgepodge, tidied up a bit, but never fundamentally reformed. And this has real consequences. In 1999, NASA lost the Mars Climate Orbiter, a $125 million spacecraft, because one engineering team at Lockheed Martin was using imperial units, specifically pound-force seconds, while NASA's Jet Propulsion Laboratory was using metric units, Newton seconds, and nobody caught the discrepancy, until the spacecraft flew far too close to Mars and either burned up or skipped off. And it wasn't the first such mistake. In 1983, an Air Canada flight ran out of fuel mid-flight because of a kilogram-to-pound conversion error during refueling, the so-called Gimli glider incident, because the pilots managed an extraordinary dead-stick landing at an abandoned airfield in Gimli, Manitoba. The plane was fine, the passengers were fine, but it easily could have been catastrophic, and the root cause was the collision between 2 measurement systems, $125 million and years of work, lost because of a unit conversion error. Measurement matters. Getting it wrong has consequences. And the story of how most of the world eventually solved this problem, how they built the measurement system you probably use every day without thinking about it, is one of the great untold adventures of modern history. It starts in the most unlikely of places, the blood and chaos of the French Revolution, and the person at the center of it, or at least one of the key figures, was a man you've probably never heard of, even though his work affects your life every single day. His name was Jean-Charles de Borda, and in the late 1780s, as France was tearing itself apart, he was quietly pushing for something that sounded almost insanely ambitious. He wanted to do something that, in its own quiet way, was as revolutionary as anything happening in the streets of Paris. He wanted to throw out every single unit of measurement in France, every local foot, every regional pound, every parish-specific bushel, and replace them all with a single, rational, universal system based not on the whims of kings or the length of anyone's arm, but on nature itself, on the earth, on something permanent and unchanging that belonged to everyone and no one. Borda was a naval officer, a mathematician, and an instrument maker of extraordinary skill. He'd designed some of the most precise measuring instruments of his era, including a repeating circle, a device for measuring angles with unprecedented accuracy. and he was a member of the French Academy of Sciences, which in the late 18th century was the most prestigious scientific body in the world. When the revolution began in 1789, the new National Assembly found itself facing a very practical problem amid all the grand ideals of liberty, equality, and fraternity. The French economy was a mess, and one of the reasons it was a mess was that nobody could agree on what anything measured. So in 1790, the Assembly asked the Academy of Sciences to come up with a new, rational system of weights and measures, and the Academy, with Borda playing a central role, took the assignment and ran with it. The first question was, what should the fundamental unit of length be based on? They considered a few options. One was the length of a pendulum that swings with a period of exactly 1 second, which is a beautiful idea because it ties length to time through the laws of physics. But the problem with the pendulum is that its period depends slightly on gravity, and gravity varies from place to place on the Earth's surface. A pendulum clock that keeps perfect time in Paris runs slightly differently in Ecuador, because the Earth bulges at the equator, and gravity is a tiny bit weaker there. So a pendulum-based unit wouldn't truly be universal. Instead, the Commission chose something grander. They decided that the fundamental unit of length, they'd call it the metre, from the Greek word metron, meaning measure, would be defined as 1/10,000,000th of the distance from the North Pole to the equator, measured along the meridian that passes through Paris. Think about the audacity of that. They were going to define their ruler by measuring the Earth itself, and then everything else would follow. The unit of area would be based on the meter. The unit of volume would be a cube 1/10 of a meter on each side. They'd call it a liter. And the unit of mass would be the mass of that volume of water at its densest temperature. Everything connected, everything rational, everything decimal. No more 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile, 10 millimeters in a centimeter, 100 centimeters in a meter, 1,000 meters in a kilometer. Clean, elegant, universal. But here's the thing, to make this work, they actually had to go out and measure a piece of the Earth's meridian, and that measurement turned into one of the most extraordinary, harrowing, and ultimately heartbreaking scientific expeditions of the 18th century. The Academy decided to measure the arc of the meridian from Dunkirk, on the northern coast of France, all the way to Barcelona, on the coast of Spain. That's roughly 1,000 kilometers, spanning about 9.5 degrees of latitude. 2 astronomers were assigned to do the work. Pierre Méchain would measure the southern section, from Barcelona up to Rodez in south-central France. Jean-Baptiste Delambre would handle the northern section, from Rodez up to Dunkirk. They expected the whole thing to take about a year. It took 7. The method they used was triangulation, and it's worth understanding because it's genuinely clever. You don't measure 1,000-kilometer distance by laying rulers end to end. That would be impossible. The terrain is mountains and rivers and forests and cities. Instead, you set up a network of triangles. You start by very precisely measuring one short baseline, a perfectly flat, straight distance of maybe 10 or 12 kilometers, using actual measuring rods laid end to end with excruciating care. Then you set up sighting stations on hilltops, church towers, and purpose-built towers, and you measure the angles of the triangles formed between these stations, using Borda's repeating circle. If you know one side of a triangle and all its angles, basic trigonometry gives you the other sides. So each triangle gives you new known distances, and you can extend the chain of triangles all the way from Dunkirk to Barcelona, calculating distances from angles the whole way. It's indirect, but it's incredibly precise, if you measure your angles carefully enough. And Delambre and Méchain were nothing if not careful. These were obsessive, meticulous men, working with the best instruments in the world, but the world they were working in was coming apart. Remember, This was revolutionary France. By the time Delambre started his measurements in 1792, the king had been deposed, the terror was beginning, and a man walking around the countryside with strange instruments, climbing church towers, and peering through telescopes, was viewed with deep suspicion. Delambre was repeatedly arrested, accused of being a spy, a royalist agent, a counter-revolutionary. He had to talk his way out of custody multiple times, showing his official papers from the Academy, papers that became increasingly dangerous to carry as the revolution devoured its own institutions. The Academy of Sciences itself was dissolved in 1793. Delambre's funding was cut off. He was briefly removed from the project entirely, then reinstated. He kept going, through political chaos, through war, through winter and summer. He kept climbing hills and measuring angles. Méchain, down in Spain, had his own troubles, and they were even worse in some ways. He had an accident in 1793. He was observing from a rooftop in Barcelona when the mechanism of a pump he was standing near malfunctioned and struck him, damaging his arm and several ribs. He spent months recovering in a foreign country, unable to work, dependent on the hospitality of Spanish astronomers, while France and Spain slid toward war. When the war came, he was effectively stranded, a French scientist on enemy soil, unable to cross the border, unable to continue his measurements, watching helplessly as the months and then years slipped by. He didn't get back to France until 1795, 3 years into what was supposed to be a one-year project, and was badly injured, spending months recovering. Spain and France went to war while he was on Spanish soil, and he was essentially trapped, unable to cross the border for years. And then something happened that would haunt Méchain for the rest of his life. He discovered a discrepancy in his measurements. When he measured the latitude of a particular station in Barcelona using 2 different methods, observing different stars from different positions, the results didn't quite agree. The difference was tiny, about 3 arcseconds, which is almost nothing in everyday terms. But for the purpose of defining a universal unit of length, it mattered. And Méchain, instead of reporting the discrepancy and letting the commission decide how to handle it, did something very human. He hid it. He fudged his data, quietly adjusting his numbers to make them look more consistent than they actually were. He didn't do this out of dishonesty in the ordinary sense. He did it because he was terrified of imperfection. Méchain was a perfectionist of the most agonizing kind, the kind who couldn't bear the thought that his measurements might contain an error, even a small one. And the weight of the project was crushing. He wasn't just measuring a distance. He was, in a very real sense, measuring the Earth in order to define how the entire world would measure everything, forever. The pressure was enormous. And under that pressure, he cracked a little. He hid his discrepancy, and then he was tortured by having hidden it. Colleagues who knew him well said the guilt ate away at him for years. He eventually went back to Spain to remeasure, to try to resolve the discrepancy, and he contracted malaria there and died in 1804, at the age of 60. The discrepancy was later understood. It was caused by a slight local deflection of the vertical, a tiny gravitational anomaly caused by the mass of nearby mountains pulling the plumb line very slightly off true. It wasn't Méchain's fault. It was the Earth itself being imperfect, refusing to be the perfect sphere that the neat calculations assumed. But by the time Méchain died, the meter had already been born. In 1799, using the best available results from the Meridian Survey, a platinum bar was constructed, exactly 1 meter long, and deposited in the French National Archives. This was the Maître des Archives, the physical embodiment of the meter, the standard against which all other meters would be compared. And alongside it, a platinum cylinder was constructed, the kilogramme des archives, representing the mass of 1 liter of water. These were the original standards, the physical objects that defined the fundamental units of the new system. And the metric system was officially adopted in France in 1799, though getting people to actually use it would take decades of persuasion, resistance, and occasionally coercion. Napoleon himself, champion of rationality in so many things, actually rolled back the metric system for a while because people hated it so much. They wanted their old familiar measures back. Napoleon's compromise system, the measures usuels, kept metric ratios but used familiar old names, trying to ease the transition. It didn't fully work. It wasn't until 1840 that the metric system became truly mandatory in France, 41 years after it was first officially adopted. Old habits, as I said, die very hard, and the resistance wasn't just stubbornness. For ordinary people, farmers, market vendors, craftsmen, their traditional measures were deeply embedded in their work and their culture. A Parisian cloth merchant knew in his bones what an awn of fabric looked like. Asking him to switch to meters was like asking him to think in a different language. The metric system was rational and elegant and superior in almost every technical way, but it was also alien, imposed from above by revolutionary authorities who had also, let's not forget, been guillotining people. The emotional resistance was real and understandable, even if the logic of the new system was overwhelming. But the idea was too powerful to stay in one country. Over the course of the 19th century, nation after nation adopted the metric system, or some version of it. The Netherlands was first, in 1816. Belgium followed, then Luxembourg, then Greece, then Colombia. Italy adopted it during unification in the 1860s. Germany adopted it in 1872, just after unification. Japan adopted it in 1885, as part of its rapid modernization during the Meiji era. Each adoption was a political act as much as a scientific one. Choosing the metric system was, in many cases, a statement about modernity, about wanting to participate in international trade and international science on equal terms. The holdouts, by and large, were the British Empire and the United States, which had their own well-established systems and the economic and political power to resist the pressure to change, drawn by the sheer elegance of having everything connect, everything based on powers of 10, everything traceable back to a definition rooted in nature. And as the system spread, a new problem emerged, one that nobody had quite anticipated, and it had to do with those platinum objects sitting in a vault in Paris. Because if the whole world's measurement system depends on one particular piece of metal, what happens if that piece of metal changes? What if it gets scratched? What if it corrodes? What if it gains or loses atoms over time? What if the building burns down? You've put the foundation of the entire system on something fragile, something physical, something that exists in one specific place. And that turns out to be a much bigger problem than anyone in 1799 imagined. It's a problem that would take 200 years to fully solve, and the solution would require some of the most extraordinary physics of the 20th and 21st centuries. But before we get there, we need to talk about another kind of measurement entirely, one that's arguably even more fundamental than length or mass, and certainly more mysterious than most people realize: temperature. Because the story of how we learned to measure hot and cold is, honestly, one of the strangest in all of science. And it starts with a guy who made thermometers in Amsterdam, and whose system of degrees seems, on its face, completely insane. Daniel Gabriel Fahrenheit was born in 1686 in Danzig, which is now Gdańsk, Poland. His parents both died on the same day when he was 15. They ate poisonous mushrooms, which is a terrible way to go, and also a terrible way to become an orphan. He was apprenticed to a merchant, ran away from his apprenticeship, and spent years wandering across Europe, visiting instrument makers, and learning the art of glass-blowing and the craft of precision instruments. By the early 1700s, he'd settled in Amsterdam and started making thermometers, and he was very, very good at it. Before Fahrenheit, thermometers were unreliable. Different thermometers gave different readings for the same temperature because there was no agreed-upon scale and no consistent method of calibration. Fahrenheit changed that. He did several important things. First, he switched from alcohol to mercury as the thermometer fluid, which was better because mercury expands more uniformly with temperature and has a higher boiling point, so you can measure hotter things. Second, and more importantly, he established fixed reference points for calibrating his instruments. And this is where it gets interesting, because his choice of reference points is the reason the Fahrenheit scale seems so arbitrary to anyone who grew up with Celsius. Fahrenheit used 3 fixed points. The first was the temperature of a mixture of ice, water, and ammonium chloride, a kind of salt, which he set as 0 degrees. Why? Because this mixture produces about the coldest temperature you can reliably achieve in a laboratory with common materials, and Fahrenheit wanted his 0 to be a genuinely cold temperature so that he wouldn't have to deal with negative numbers in everyday weather. His second fixed point was the freezing point of pure water, which he set at 32 degrees. And his third was human body temperature, which he originally placed at 96 degrees. Now, 96 might seem like an odd number, but there's a theory that Fahrenheit liked it because 96 is divisible by many small numbers, 2, 3, 4, 6, 8, 12, which made it easy to mark out intermediate points on his scale by repeatedly halving intervals. Others think he just measured his own body temperature on a cold day and got 96, and that was that. We're not entirely sure. The modern measurement of average human body temperature on the Fahrenheit scale is 98.6, which doesn't match Fahrenheit's original, but that discrepancy is probably because Fahrenheit's thermometers, good as they were, weren't perfectly accurate. Now, there's something charming about Fahrenheit's approach, even if the resulting numbers seem random to modern eyes. He was trying to solve a practical problem. He wanted a scale that would cover the range of temperatures people actually encountered in daily life, from the coldest winter day to the hottest fever, and he wanted the numbers to be positive and manageable. And honestly, for weather, Fahrenheit's scale has a certain elegance that Celsius doesn't. 0 Fahrenheit is seriously cold. 100 Fahrenheit is seriously hot. The range from 0 to 100 covers almost exactly the range of outdoor temperatures that most people on Earth experience. On the Celsius scale, that same range runs from about -18 to about 38, which doesn't have the same neat symmetry, but that's aesthetics, not science. So that's the Fahrenheit scale. It's a little weird. 0 isn't the coldest thing possible. It's just the coldest you could easily make in a lab in 1720. Water freezes at 32, which isn't a nice round number. Water boils at 212, which isn't a nice round number either. But the scale works, it's consistent, and it's what most people in the United States and a few other countries still use every day. Then along came Anders Celsius, a Swedish astronomer, who in 1742 proposed a different scale. Celsius took what seemed like the 2 most obvious reference points, the freezing point of water and the boiling point of water, and divided the interval between them into 100 degrees. Clean, simple, rational. 0 degrees is freezing. 100 degrees is boiling. Everything in between is a smooth, linear scale. But here's a fun detail that most people don't know. Celsius originally had the scale backwards. In his original proposal, 0 was the boiling point and 100 was the freezing point. He ran it upside down. It was Carl Linnaeus, the great Swedish botanist and taxonomist, who flipped it to the version we use today. Or possibly it was Celsius's colleague Morten Strömer. The historical record is a bit murky. Either way, the Celsius scale as we know it, with 0 for freezing and 100 for boiling, became the standard for most of the world. But here's what's really fascinating about both of these scales, and it's something that reveals a deep truth about measurement in general. Both Fahrenheit and Celsius defined their scales using reference points that are, ultimately, arbitrary. Why should 0 be the temperature of an ice-salt mixture? Why should it be the freezing point of water? Why water at all? What makes water special? And the answer, scientifically speaking, is nothing. Water is convenient because it's everywhere, and its phase transitions, freezing and boiling, are easy to observe and reproduce. But there's nothing fundamental about it. These are practical choices, not physical ones. And this is where a man named William Thomson comes in, Lord Kelvin, as he later became known. And he's one of those extraordinary figures of 19th century science who deserves to be far more famous than he is. Thomson was born in Belfast in 1824, moved to Glasgow at a young age, and was a professor of natural philosophy at the University of Glasgow from the remarkable age of 22, an appointment that would be extraordinary today and was almost unheard of then. He held that position for 53 years, which is itself a kind of measurement of dedication. He was knighted, then made a baron, Lord Kelvin of Largs, and he published over 600 scientific papers. He was a prodigy, and he contributed to an astonishing range of fields: thermodynamics, electromagnetism, the transatlantic telegraph cable, the age of the Earth, fluid dynamics. But for our story tonight, what matters is what he did for temperature. Thomson asked, is there a natural 0? Not an arbitrary 0, not a 0 defined by salt water or ice, but a 0 that the universe itself defines? And the answer, it turns out, is yes. It comes from the behavior of gases. Here's the basic observation. If you take a gas, any gas, it doesn't matter which one, and you cool it down while keeping the pressure constant, it contracts. Its volume shrinks, and the relationship is remarkably simple and linear. For every degree Celsius you cool it, it loses a fixed fraction of its volume. If you plot volume against temperature, you get a straight line. And here's the fascinating part. If you extend that line downward, projecting it toward colder and colder temperatures, it hits 0 volume at the same temperature, regardless of which gas you started with. That temperature is about -273.15 degrees Celsius. It was the French physicist Guillaume Amonton who first noticed this trend back around 1702, and the idea was refined over the next century and a half by scientists including Johann Heinrich Lambert and Joseph Louis Gay-Lussac. Gay-Lussac's law, published in 1802, though the work was actually done by Jacques Charles 15 years earlier and never published, which is why the same relationship is also called Charles's law. And yes, the history of science is full of these attribution tangles. Gay-Lussac's law stated that the volume of a gas at constant pressure changes by 1/267th of its volume at 0 Celsius for each degree of temperature change. Later, more precise measurements revised that fraction, and the extrapolated 0 point settled at -273.15 degrees. Every gas, if it could keep behaving ideally, would shrink to nothing at the same temperature. Now, real gases don't actually do this. They liquefy and then solidify long before they get that cold. But the extrapolation is consistent and universal. That temperature, -273.15 Celsius, is absolute 0. It's the temperature at which the thermal motion of atoms and molecules reaches its minimum, the point where there's essentially no thermal energy left to extract. It's nature's own zero point, and it's the foundation of the Kelvin scale. Thomson proposed this scale in 1848, and it's elegantly simple. The Kelvin scale uses the same degree size as Celsius, so a difference of 1 Kelvin is the same as a difference of 1 degree Celsius, but it starts at absolute zero, instead of at the freezing point of water. So absolute zero is 0 kelvins. Water freezes at 273.15 kelvins. Water boils at 373.15 kelvins. Room temperature is about 293 kelvins. There are no negative temperatures on the Kelvin scale because you can't go below absolute zero. There's nowhere colder to go. And this isn't just a matter of convention, like choosing whether to start counting from 1 or from 0. Absolute zero is a physical reality. As you approach it, strange and wonderful things happen. Gases liquefy, then solidify. Helium, the most stubborn of all elements, finally condenses into a liquid at about 4 kelvins, minus 269 degrees Celsius. And if you cool it further, to about 2 kelvins, it becomes a superfluid, flowing without any friction at all, creeping up the sides of containers, behaving in ways that defy everyday intuition. Some materials become superconductors near absolute zero, losing all electrical resistance. The quantum nature of matter, normally hidden beneath the thermal noise of atomic jiggling, becomes visible and dominant. Absolute zero is where the classical world gives way entirely to the quantum one. And this matters, this shift from arbitrary to absolute, because it reflects a deeper principle that runs through the whole history of measurement. The best measurement systems are the ones that are anchored to something fundamental about nature, something that doesn't depend on a particular material, or a particular location, or a particular political decision. The Fahrenheit and Celsius scales are tied to properties of water. The Kelvin scale is tied to the laws of thermodynamics themselves. And as we'll see, this same impulse, this drive to anchor measurement to something universal and unchanging, is the thread that connects the French Academy measuring the Earth's meridian in the 1790s to the extraordinary redefinition of all our fundamental units that happened in 2019. The whole history of measurement is, in a sense, the story of humanity reaching for increasingly stable, increasingly fundamental things to attach our numbers to. But that's getting ahead of ourselves. Because there's another kind of measurement we need to talk about, one that turned out to be so important, so practically urgent, that it drove some of the most remarkable feats of engineering and science in the 17th and 18th centuries. And unlike length or temperature, this one had life and death consequences every single day. People were dying, drowning, starving, wrecking their ships on rocks, because they couldn't measure one particular thing accurately enough. And that thing was time. Or more precisely, the combination of time and position that would tell a sailor exactly where they were on the open ocean. This is the story of the longitude problem, and it's one of the greatest measurement stories ever told, and it centers on a self-taught clockmaker from Yorkshire named John Harrison, a man who spent his entire adult life trying to solve a problem that the greatest scientists of his age said couldn't be solved the way he wanted to solve it. And he was right, and they were wrong. And the story of how that played out is both inspiring and infuriating. So let's set the stage. It's the early 1700s, and maritime navigation is the most important technical challenge in the world. Nations that can navigate accurately can trade, can build empires, can project military and commercial power across oceans. Nations that can't lose ships, lose crews, lose wars. And the toll was horrific. In 1707, a fleet of British warships under Admiral Sir Cloudesley Shovel miscalculated their longitude returning home from the Mediterranean, ran onto the rocks of the Scilly Isles off the southwest tip of England, and 4 ships went down, killing somewhere between 1,400 and 2,000 sailors. It was one of the worst maritime disasters in British naval history, and it was caused, at bottom, by not knowing where they were. That disaster, more than anything else, focused British minds on the longitude problem and helped lead to the Longitude Act 7 years later. And the central problem of navigation at sea was this: figuring out your latitude, how far north or south you are, was relatively easy. You could measure the angle of the sun at noon, or the angle of certain stars above the horizon at night, and with some tables and basic math, you'd know your latitude pretty accurately. Sailors had been doing this for centuries, but longitude, how far east or west you are, was a completely different matter. There was no simple celestial observation that would give it to you directly, and without knowing your longitude, you were essentially guessing where you were in the east-west direction. You knew you were somewhere along a particular parallel of latitude, but you didn't know where along that line. And that's a recipe for disaster. The basic problem is actually easy to state. Longitude is fundamentally a matter of time. The Earth rotates 360 degrees in 24 hours, which means it rotates 15 degrees every hour. So if you know the exact time at some reference location, let's say Greenwich, England, and you know the exact local time wherever you are, then the difference between those 2 times tells you your longitude. If your local noon happens 2 hours after Greenwich noon, you're 30 degrees west of Greenwich. Simple, but here's the catch. You need to know the time at Greenwich with great accuracy, and you need to know it while you're on a ship in the middle of the ocean, thousands of miles from Greenwich, being tossed by waves and battered by storms, and subjected to wild swings in temperature and humidity. You need a clock that keeps accurate time under those conditions, and in the early 1700s, no such clock existed. The clocks of the era were pendulum clocks, and the story of the pendulum clock itself is worth a brief tangent, because it begins with one of the most famous moments in the history of science, possibly apocryphal, but too good not to tell. According to tradition, sometime around 1583, the young Galileo was sitting in the Cathedral of Pisa, watching a large chandelier swing back and forth after it had been set in motion, perhaps by a draft or by a sacristan lighting the candles. And Galileo noticed something peculiar. Whether the chandelier was swinging in wide arcs or narrow ones, each swing seemed to take the same amount of time. He timed it using the only clock he had available, his own pulse. And he found that the period of the swing was indeed roughly constant, regardless of the amplitude. This property, called isochronism, is what makes pendulums useful for timekeeping. A long swing takes the same time as a short swing. That means the pendulum naturally keeps a steady beat, even as its swings gradually diminish due to air resistance and friction. The clocks of the era were pendulum clocks. Christian Huygens, the great Dutch physicist and mathematician, had built the first practical pendulum clock in 1656, turning Galileo's observation into a working timepiece. And it was a magnificent piece of engineering. A pendulum swings with a period that depends on its length and the local gravitational acceleration, and almost nothing else. If you make the pendulum the right length, it'll tick off seconds with remarkable regularity. On land, in a stable building, a well-made pendulum clock could keep time to within a few seconds a day. That's very, very good. But on a ship, forget it. The rolling and pitching of the ship would throw the pendulum off completely. Huygens actually tried to build marine pendulum clocks, using clever suspension systems to isolate the pendulum from the ship's motion. They didn't work well enough. Other approaches were tried, spring-driven watches, for instance, but the springs of the era were affected by temperature changes, which altered their elasticity and threw off the timekeeping. A clock that was accurate enough for longitude determination had to keep time to within about 3 seconds a day over the course of a voyage that might last months. That's extraordinarily demanding. Nobody could do it. The problem was so urgent, and the consequences of not solving it so severe, that the British government took an extraordinary step. In 1714, Parliament passed the Longitude Act, which established a board of longitude and offered enormous cash prizes to anyone who could demonstrate a practical method of determining longitude at sea. The top prize was £20,000, equivalent to several $1,000,000 today. It was one of the largest prizes ever offered for solving a scientific problem, and it attracted everyone from serious scientists to complete crackpots. The scientific establishment's preferred solution was astronomical. The idea was to use the positions of celestial objects, particularly the moon, as a kind of universal clock. The moon moves against the background of fixed stars at a predictable rate, so if you could accurately measure the moon's position relative to certain stars, and if you had sufficiently precise tables predicting where the moon would be at any given time, as seen from Greenwich, you could work backward to figure out what time it was at Greenwich. This is called the method of lunar distances, and it was championed by some of the most powerful figures in British science, including the Astronomer Royal, Neville Maskelyne. The method worked in principle, but it was incredibly laborious. Each observation required about 4 hours of complex mathematical calculation, and it depended on having a very accurate theory of the moon's motion, which was one of the hardest problems in celestial mechanics. Newton himself had struggled with it. And then there was Harrison. John Harrison was born in 1693 in Foulby, Yorkshire, the son of a carpenter. He had almost no formal education. He taught himself clockmaking, and from the beginning, he was an extraordinary craftsman, meticulous, inventive, obsessive about precision. As a young man, he built a series of remarkable wooden clocks, including a long case clock made almost entirely of wood, with wooden gears and a grasshopper escapement of his own design. These clocks were astonishingly accurate for their time, and they incorporated innovations that addressed the two great enemies of precision timekeeping: friction and temperature variation. Harrison invented a device called the gridiron pendulum, which used alternating rods of brass and steel that expanded and contracted at different rates with temperature changes, keeping the effective length of the pendulum constant despite temperature fluctuations. He was solving problems that the finest clockmakers in London hadn't cracked. In 1730, Harrison went to London to present his idea for a marine timekeeper to the Board of Longitude. He was directed to George Graham, the most famous clockmaker in England, and Graham was so impressed that he gave Harrison a personal loan to build his first marine clock. It took Harrison 5 years. The result, now known as H1, was a massive, beautiful, bizarre-looking machine. It weighed over 75 pounds and used a pair of connected balances instead of a pendulum, so it would be unaffected by the ship's motion. It also used Harrison's anti-friction devices and temperature compensation. It was tested on a voyage to Lisbon in 1736, and it performed well enough to impress the Board of Longitude, though not well enough to win the prize. Harrison went back to work. He built H2, an even larger and heavier machine, incorporating improvements but still fundamentally the same approach: a big, heavy timekeeper designed to be impervious to the ship's motion. H2 was never actually tested at sea because Harrison, his own harshest critic, kept finding things he wanted to improve. He was the kind of craftsman who couldn't stop tinkering, couldn't stop seeing flaws that nobody else noticed. He worked on H2 from 1737 to about 1740, and then moved on to H3, which represented a completely different approach to temperature compensation and friction reduction. Then H3, which took him 19 years of painstaking refinement, addressing every tiny source of error he could identify. And then, in a remarkable shift, he abandoned the large marine clock approach entirely and built H4, a watch, a pocket watch really, just 5 inches in diameter, and it was this small, elegant device, completed in 1759, that finally solved the problem. H4 was tested on a voyage to Jamaica in 1761, and when they arrived after 81 days at sea, the watch was off by only 5 seconds. 5 seconds. That translates to a longitude error of about 1¼ minutes of arc, which is far, far better than the longitude act required. Harrison had done it. He'd built a clock accurate enough to determine longitude at sea. But here's where the story gets frustrating. The Board of Longitude, dominated by astronomers who favored the lunar distance method, refused to award Harrison the full prize. They kept changing the rules, demanding more trials, more demonstrations. Nevil Maskelyne, the Astronomer Royal and a member of the board, was openly hostile to Harrison's approach. He considered the mechanical solution inelegant and was deeply invested in the astronomical method. Harrison fought for his prize for years, growing old and bitter. He appealed to King George III, who tested H5, another of Harrison's watches, personally, and declared it accurate. Finally, in 1773, when Harrison was 80 years old, Parliament awarded him a direct payment, though it was technically not the longitude prize itself, the board having never formally granted it. Harrison died 3 years later, in 1776. He'd spent the best part of 50 years solving one measurement problem, and he'd had to fight every step of the way. But the impact of what he'd done was immeasurable. Accurate marine chronometers, built on Harrison's principles, became standard equipment on ships throughout the 19th century. Captain Cook carried a copy of H4, made by the clockmaker Larcom Kendall, on his second and third voyages, and he praised it extravagantly. Reliable longitude determination transformed navigation, trade, and global communication. It made the British Empire possible in its most expansive form. By the mid-19th century, every Royal Navy vessel carried chronometers, and the chronometer-making industry, centered in London, with firms like Arnold, Earnshaw, and Frodsham, was one of the most precision-demanding industries in the world. A single marine chronometer might contain hundreds of handcrafted parts, each made to tolerances that pushed the limits of what human hands and eyes could achieve. The best chronometers could keep time to within a fraction of a second per day, even in the tropics, even through storms, even through the constant vibration and shock of life at sea. They were, in their way, the most precise portable instruments in the world, and they remained the primary tool for oceanic navigation until the advent of electronic navigation systems in the mid-20th century. That's nearly 200 years of service, all flowing from one stubborn Yorkshire clockmaker's refusal to accept that the problem couldn't be solved. And it demonstrated something profound about measurement. Sometimes the most important thing you can measure isn't a distance or a weight, but a duration. And getting that duration precisely right can save thousands of lives. And Harrison's story illustrates something beautiful about the act of measurement itself. The longitude problem wasn't just a question about where you are. It was a question about how precisely you can know the world, and how that precision can save lives. Every advance in measurement has this dual character. It's abstract and practical, theoretical and deeply human. The ability to measure longitude saved thousands of sailors from drowning. The ability to measure a cesium atom's vibration frequency would later give us GPS. The ability to measure the Planck constant would redefine the kilogram. Each advance in precision opens doors that nobody anticipated. And Harrison's story also contains another lesson that runs through the whole history of measurement. the tension between theoretical and practical approaches, between the scientists who want an elegant solution and the craftsmen who just want something that works. That tension never really goes away. It shows up again and again, in different forms, as measurement becomes more and more central to industrial civilization. Because after the era of exploration, something new was coming, something that would place entirely different demands on the precision and standardization of measurement. The Industrial Revolution was about to transform the world, and it needed measurements that were not just accurate, but interchangeable, not just consistent within one workshop, but identical across factories, across countries, across oceans. And that shift, from measurement as a local practice to measurement as a global infrastructure, is one of the most important and least appreciated stories of the modern world. Here's the problem that the Industrial Revolution created. Before mass production, things were made by hand, one at a time, by skilled craftsmen. If you needed a replacement part for a musket, or a steam engine, or a textile machine, a craftsman would custom make it, filing and fitting it by hand until it worked with the specific machine it was going into. Every part was unique. Every assembly was a one-off. And that worked fine when production was small scale, but it was completely unworkable when you needed to make thousands or millions of identical things. The solution was interchangeable parts, the idea that any instance of a particular component should be so identical to every other instance that you can swap them freely without any hand fitting. Pull a broken part out, drop a new one in, and it works. This idea, which seems so obvious now that it hardly needs stating, was revolutionary in the late 18th and early 19th centuries, and it depended entirely on one thing: measurement precision. If every bolt has to be the same as every other bolt, then every bolt has to be made to the same dimensions, within very tight tolerances. And that means you need gauges, reference standards that define exactly how big things are supposed to be, to a level of precision that craftsmen of earlier eras would have found absurd. The push for interchangeable parts is often associated with Eli Whitney and the manufacture of muskets for the U.S. Army in the early 1800s, though historians now think Whitney's claims about achieving true interchangeability were exaggerated. The real breakthroughs came later, from people like John Hall at the Harper's Ferry Armory, and from the system of manufacturing that emerged in the Connecticut River Valley in the mid-19th century. What the British, impressed and a little alarmed when they saw it at the 1851 Great Exhibition in London, called the American System of Manufacturing. This system used specialized machine tools, milling machines, lathes, drilling machines, each set up to perform one specific operation with great precision, guided by jigs, fixtures, and gauges that ensured every part came out the same. And at the heart of it all were the gauges. Without them, none of it works. And the precision demanded by interchangeable manufacturing kept ratcheting upward. In the early 1800s, a tolerance of a 50th of an inch, about half a millimeter, was considered fine work. By mid-century, that was routine, and the frontier had moved to 1/1000th of an inch. By the end of the century, Joseph Whitworth, the great British engineer who standardized screw threads and built some of the finest machine tools of the era, could measure to 1/1000th of an inch. 1/1000th. That's about 25 nanometers. Whitworth built a measuring machine that used a feel method. The operator would slide a precision flat across the workpiece and feel for contact with such sensitivity that differences of 1/1000th of an inch could be detected. It's hard to wrap your head around that kind of precision, achieved with mechanical tools and the trained hands of a Victorian craftsman. And here's the thing about precision that people often don't appreciate. It's recursive. To make a precise machine, you need precise measuring tools. To make precise measuring tools, you need even more precise machines to make them. Every generation of precision enables the next. The lathe that makes the gauge, that checks the part that goes into the engine, that drives the factory that makes the next, better lathe. It's precision, building on precision, all the way up. Whitworth understood this deeply. He used to say that the three essential things in mechanical engineering were a true plane, a straight line, and accurate measurement, and he spent his career perfecting all three. His method for producing a perfectly flat surface, rubbing three plates against each other in pairs so that the only shape all three can share is a true plane, is still used in precision workshops today. It's a simple idea, and it's brilliant, and it came from a man who understood that you can't measure better than you can make, and you can't make better than you can measure. Now, around the same time that manufacturing was demanding ever greater dimensional precision, an entirely new category of measurement was emerging, and it was just as consequential. Electricity. The early and mid-19th century saw an explosion of discovery about electrical phenomena. Volta's battery, Ampere's work on currents and magnetic fields, Ohm's law relating voltage, current, and resistance, Faraday's discovery of electromagnetic induction. All of this was enormously exciting and enormously promising, but it posed a measurement problem that was, in some ways, entirely novel. Think about it. Length, mass, and time are things you can directly perceive. You can hold a ruler, you can lift a weight, you can feel time passing. But voltage, current, resistance, you can't see an ampere, you can't hold a volt. These are abstract quantities defined by their effects, the force between current-carrying wires, the rate of flow of electric charge, the opposition to that flow. To measure them, you need instruments that convert electrical quantities into something visible. The deflection of a needle, the heating of a wire, the deposition of metal in an electrolysis cell. And those instruments need to be calibrated against something. But against what? There were no reference standards for electrical quantities. Every laboratory had its own units, its own standards, its own instruments, calibrated in its own way. A measurement of resistance made in one lab couldn't be meaningfully compared with a measurement made in another. This was not just an academic inconvenience. It was a crisis for what was quickly becoming the most transformative technology of the 19th century. The telegraph was spreading across the world. Submarine cables were being laid across the Atlantic, and the performance of those cables depended critically on the electrical properties of the materials they were made of, the resistance of the copper conductor, the capacitance of the insulation, the leakage of current through imperfect materials. When William Thomson, Lord Kelvin, our old friend from the temperature story, worked on the first transatlantic telegraph cable in the 1850s and 1860s, one of the biggest challenges was making reliable electrical measurements. The cable failed multiple times, partly because of manufacturing variations that better measurement could have caught. So there was intense pressure from both science and industry to establish international standards for electrical units, and this led to a series of remarkable international congresses and conferences in the 1860s, 1870s, and 1880s, where scientists from different countries came together to argue about how to define the ohm, the volt, the ampere, and the other electrical units. These were contentious, politically charged meetings. National prestige was at stake, and every country wanted its own approach to prevail. The Germans had one set of resistance standards. The British had another. The French had their own system of electromagnetic units, derived from the metric system. Reconciling all of this was a massive diplomatic and scientific undertaking. And this is where the story of measurement takes a genuinely international turn, because it wasn't just electrical units that needed standardization. By the 1870s, the metric system was spreading rapidly, but different countries were using slightly different versions, calibrated against slightly different copies of the French standards. There was a growing recognition that what the world needed was not just a good system of units, but an international infrastructure for maintaining, comparing, and disseminating those units. A permanent institution, with authority recognized by all participating nations, that would serve as the ultimate arbiter of what a meter, a kilogram, a second actually meant. In 1875, 17 nations signed the Treaty of the Mètre, the Convention du Mètre, in Paris. And I want you to appreciate what a remarkable moment this was, because international cooperation in the 1870s was not easy. Europe had just come through the Franco-Prussian War. National rivalries were intense. And yet, here were 17 nations, including recent enemies France and Germany, agreeing to submit their measurements to a common authority, to trust a shared infrastructure, to accept that science required cooperation even when politics demanded competition. It was one of the first modern examples of what we'd now call international scientific governance, and it worked. It's still working. As of today, the Treaty of the Mètre has been signed by over 60 nations, and the BIPIM continues to operate from the same site outside Paris, coordinating measurement standards for most of the world. It was one of the first modern international treaties dedicated to scientific cooperation, and it established several things that still exist today. First, it created the Bureau International des Poids et Mesures, the International Bureau of Weights and Measures, known by its French acronym BIP, with a permanent headquarters and laboratory at the Pavillon de Breteuil in Sèvres, just outside Paris. Second, it established the Conférence Générale des Poids et Mesures, the General Conference on Weights and Measures, which meets periodically to make decisions about the international system of units. And third, it authorized the creation of new international prototype standards for the meter and the kilogram, made from a platinum-iridium alloy, 90% platinum, 10% iridium, chosen for its hardness, stability, and resistance to corrosion. These new prototypes were extraordinary objects. The International Prototype Meter was an X-shaped bar, about 1 meter long, with fine lines etched near each end, the meter being defined as the distance between those lines at a specified temperature. And the International Prototype Kilogram, which would become one of the most famous objects in the history of science, was a cylinder, about 39 millimeters in both diameter and height, polished to a mirror finish. It was placed under 3 nested glass bell jars in a climate-controlled vault at the BIPIM, and it was the kilogram. Not a representation of the kilogram, not a copy of the kilogram. It was the kilogram by definition. If that cylinder had a particular mass, then that mass was exactly 1 kilogram, because that's what the word meant. Copies were made and distributed to the signatory nations. The United States received its copies in 1889, K20 and K4. They were designated. France had its own national copies. Germany, Russia, Japan. Everyone who signed the treaty got their own carefully calibrated cylinders, each compared against the international prototype and certified to match it within a few micrograms. And for over a century, this system worked. Whenever anyone, anywhere in the world, needed to know what a kilogram was, the chain of calibration led back to that one cylinder under glass in Sèvres. But the system had a weakness, a fundamental fragility that became increasingly apparent as measurement science advanced. And this is where the story takes what I think is its most fascinating turn, because the problem with the kilogram wasn't just a practical inconvenience. It was a philosophical crisis at the heart of measurement itself. Because here's the question: if the International Prototype Kilogram defines what a kilogram is, then how do you know if it's changing? You can't weigh it against anything, because it is the standard against which everything else is weighed. If it loses atoms, through handling, through cleaning, through the inevitable wear of existing in a physical world, then by definition, it still weighs exactly 1 kilogram. It's everything else that has changed. The whole universe of calibrated masses shifts, invisibly, because the reference point has moved. And this is exactly what seems to have happened. When scientists periodically brought the national prototype kilograms back to Sèvres for comparison with the international prototype, the copies had diverged. Over a century, the gap between some of the copies and the international prototype had grown to about 50 micrograms. That's 50 millionths of a gram, roughly the mass of a fingerprint. Now, 50 micrograms sounds like nothing, and in everyday life, it is nothing. But in precision science, in pharmaceutical manufacturing, in semiconductor fabrication, in any field where you need to know masses with extreme accuracy, it matters. And worse, there was no way to know whether the copies had gained mass, or the international prototype had lost it, or some combination of both. The standard was drifting, and because it was the standard, there was no higher authority to appeal to. And there was another unsettling discovery. When the copies that had been distributed in 1889 were brought back for their periodic comparison, roughly every 40 years, the copies from different countries didn't all agree with each other, and their relationship to the international prototype had shifted. Some copies seemed to have gained about 30 to 50 micrograms relative to the international prototype, or had the international prototype lost 30 to 50 micrograms. There was simply no way to tell. The detective was also the suspect. You can't investigate the standard using the standard. This drove metrologists absolutely crazy. It's a genuinely unsettling situation when you think about it. The entire world's mass measurement system was anchored to a physical object, and that object was, by its very nature, unknowable. You couldn't check it. You couldn't verify it. You just had to trust it, even as the evidence suggested it was slowly changing. It was like having a ruler that's getting shorter, but you can't tell because every other ruler is calibrated against it. And so, starting in the late 20th century, the metrology community, that's the community of scientists who study measurement itself, began a decades-long effort to redefine the kilogram in a way that would free it from any physical object. They wanted to tie it to a fundamental constant of nature, something that is, as far as we know, truly invariant, the same everywhere in the universe, the same at every point in time, unchangeable and unchanging. And while they were at it, they wanted to do the same for the other base units too. The meter, the second, the ampere, the Kelvin, the mole, the candela. They wanted to rebuild the entire international system of units from the foundations up, anchoring everything to the constants of physics. But before we get to how they did that, and they did in 2019, in what is honestly one of the most quietly revolutionary moments in the history of science, let's talk about the unit that was redefined first, and the incredible story of how it happened. Because the second, the fundamental unit of time, had its own remarkable journey from astronomical observations to the inside of an atom. For most of human history, the second was defined astronomically. A day is one rotation of the Earth. An hour is 1/24th of a day. A minute is 1/60th of an hour. A second is 1/60th of a minute. So a second is 1/86,400th of a day. Easy enough. But the Earth's rotation isn't perfectly constant. It's actually slowing down, very gradually, mostly because of tidal friction. The gravitational interaction between the Earth and the Moon transfers energy from the Earth's rotation into the Moon's orbital motion, causing the Moon to slowly drift away and the Earth to slowly spin down. The days are getting longer by about 2-3 milliseconds per century. That doesn't sound like much, but over decades and centuries, it adds up. And if your definition of the second is based on the Earth's rotation, then the second itself is slowly changing. By the mid-20th century, physicists needed a definition of the second that was far more stable than anything the Earth's rotation could provide. And the breakthrough came from an entirely unexpected direction, from atomic physics. In 1955, Louis Essen and Jack Perry, at the National Physical Laboratory in England, built the first practical cesium atomic clock. And it worked by exploiting a beautifully precise property of cesium atoms. Here's the basic idea. Every atom has a set of discrete energy levels. Remember quantum physics, how electrons can only exist in certain specific orbits, certain allowed energy states? Cesium-133 atoms have a particular transition, a specific jump between two very closely spaced energy levels in the ground state of the atom that produces or absorbs microwave radiation at an extraordinarily precise and stable frequency. That frequency is 992,631,770 cycles per second. Every cesium-133 atom in the universe, whether it's in a laboratory in Paris, floating in interstellar space, or sitting on the surface of a planet orbiting a distant star, vibrates at this same frequency. Not approximately the same, exactly the same. It's one of the most reliable facts in all of physics. It doesn't depend on temperature, or pressure, or where you are, or when you are. It's a property of the atom itself, determined by the fundamental constants of physics. In 1967, the General Conference on Weights and Measures made it official. 1 second is the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. That's a mouthful, but what it means is profound. The second is no longer defined by the Earth's rotation, which is variable and unpredictable. It's defined by the behavior of atoms, which is universal and constant. A cesium atom in a lab in Tokyo vibrates at the same frequency as one in Paris or one in orbit around Jupiter. The second has been freed from the Earth and anchored to nature at its most fundamental level, and the precision of cesium clocks is staggering. The best cesium fountain clocks, developed in the 1990s and 2000s, are accurate to about 1 second in 100 million years. That's 1 part in about 10 to the 15th. To put that in perspective, if a cesium fountain clock had been started at the time of the dinosaurs, 66 million years ago, it would be off by less than a minute today. Or to put it another way, if you could measure distances with the same relative precision, you could determine the distance from the Earth to the Sun, about 93 million miles, to within about the width of a human hair. And more recent atomic clocks, optical clocks, which use transitions at much higher frequencies in atoms, like strontium, ytterbium, and aluminum, are even better. Some of the best optical clocks now operating would not gain or lose a second in the entire age of the universe, roughly 14 billion years. That is an almost incomprehensible level of precision. And it's not an academic exercise. It has profound practical consequences. Let's talk about GPS, because this is where absurdly precise time measurement directly touches your everyday life. The Global Positioning System works by measuring time with extraordinary accuracy. Each GPS satellite carries multiple atomic clocks on board, and the satellite continuously broadcasts the time according to those clocks, along with information about the satellite's position. Your GPS receiver picks up signals from at least 4 satellites, notes the time each signal was sent and the time it arrived, and calculates the distance to each satellite based on the speed of light times the travel time. From those distances, it calculates your position. Simple in principle. But think about the precision required. Light travels about 1 foot in a nanosecond. 1/1000th of a second. So if your timing is off by even 100 nanoseconds, your position is off by about 100 feet. To get the meter-level accuracy that modern GPS provides, you need nanosecond-level time precision across a constellation of satellites orbiting at 20,000 kilometers altitude. And here's where it gets really interesting. Einstein's theory of relativity, which we've touched on indirectly tonight without diving into, makes a very specific prediction about clocks and gravity. Clocks that are deeper in a gravitational field tick more slowly. A clock on the ground runs slightly slower than a clock in orbit because the ground clock is closer to the Earth's center of mass, deeper in the gravitational well. The effect is tiny. For GPS satellites, it amounts to about 45 microseconds per day. But 45 microseconds is 45,000 nanoseconds, and if you're trying to measure positions to within a few meters, a 45,000 nanosecond error would be catastrophic. Your GPS would drift by about 10 kilometers per day. It would be useless within hours. So the clocks on GPS satellites are deliberately adjusted to account for general relativistic effects. They're actually set to tick at a slightly different rate before they're launched, so that once they're in orbit and experiencing less gravitational time dilation, they'll match the clocks on the ground. This is not theoretical hand-waving. This is engineering. If you don't correct for general relativity, GPS doesn't work. Every time you use Google Maps to navigate to a restaurant, every time an Uber knows where to pick you up, every time a precision-guided agricultural system plants seeds to within a centimeter of where they should go, you're relying on Einstein's 1915 theory of general relativity to make the measurement accurate. That's one of those facts that, once you know it, makes the world feel a little more extraordinary than it did before. And there's a special relativity correction too, working in the opposite direction. The satellites are moving fast, about 14,000 kilometers per hour, and special relativity says that moving clocks run slow relative to stationary ones. This effect subtracts about 7 microseconds per day from the gravitational effect, giving a net correction of about 38 microseconds per day. Both corrections, general and special, have to be applied, and they have been experimentally confirmed to extraordinary precision. It's one of the most beautiful practical validations of relativity that exists. So, by the early 21st century, the second had been spectacularly redefined, freed from astronomical observation, and anchored to atomic physics. The meter had been redefined too. We should talk about that, because it happened in 1983, and it's a story worth telling. For decades, the meter had been defined by that platinum iridium bar in Sèvres, a definition that required you to physically travel to France, or at least to obtain a carefully calibrated copy if you wanted to know what a meter was. In 1960, the General Conference took a step away from the artifact by redefining the meter using the wavelength of a specific orange-red spectral line from Krypton 86 atoms. A specific orange-red spectral line. But even that wasn't stable or precise enough for the increasingly demanding needs of modern science. So in 1983, the General Conference made a radical decision. They defined the speed of light in vacuum to be exactly 299,792,458 meters per second. Not approximately. Exactly. And then they defined the meter as the distance light travels in vacuum in 1/299,792,458th of a second. Think about what that means. The speed of light is no longer something you measure. It's a defined constant, an exact number by decree, and the meter is now derived from the second and the speed of light. You don't need a bar in a vault. You don't need a particular wavelength of light from a particular atom. You need a clock and the speed of light, and you can reconstruct the meter anywhere in the universe. It's a definition that travels. It's a definition that belongs to physics itself, not to any artifact or any institution. And that same logic, define the unit by fixing a fundamental constant, is what drove the extraordinary redefinition that happened in 2019. But to tell that story properly, we need to talk about a very special piece of equipment, a device of almost unbelievable ingenuity that made it possible to redefine the kilogram without any physical artifact at all. It's called the Kibble balance, and if you've never heard of it, that's not surprising. It's one of the most important scientific instruments of the 21st century, and almost nobody outside the metrology community knows it exists. The Kibble balance was invented by Brian Kibble, a British physicist working at the National Physical Laboratory in Teddington, England. Kibble was a quiet, methodical man, a person of legendary precision, even in a field defined by precision. Colleagues remembered him as someone who would spend days tracking down a source of error that other scientists would have dismissed as insignificant, who insisted on understanding every aspect of his instruments down to the last wire and screw. In 1975, he came up with an idea that was, in retrospect, a stroke of genius. The idea was to create a balance that could compare a mechanical force, the weight of a mass in a gravitational field, against an electromagnetic force, with extraordinary precision. And the key insight was that by doing this comparison very carefully, you could relate mass to fundamental constants of physics, specifically to the Planck constant. Here's the simplified version of how it works, and I'll try to keep this intuitive, because the actual physics involves some serious quantum mechanics. Imagine a traditional balance scale, the kind with two pans, one on each side. On one side, you put the object whose mass you want to determine. On the other side, instead of putting known weights, you use an electromagnetic force. You have a coil of wire in a magnetic field, and when you run an electric current through the coil, it experiences a force. That's basic electromagnetism, the same principle that makes electric motors work. By carefully measuring the current and the magnetic field, you can calculate the electromagnetic force precisely, and when you adjust it until it exactly balances the weight of the mass, you've measured the mass in terms of electrical quantities. But here's where the quantum mechanics comes in, and where it gets really clever. The Kibble balance operates in two modes. In the first mode, the weighing mode, you balance the mass against the electromagnetic force, as I just described. In the second mode, the velocity mode, you move the coil through the magnetic field at a known velocity and measure the voltage it generates. By combining the measurements from both modes, the characteristics of the coil and the magnetic field cancel out. You don't need to know them separately. What you're left with is a relationship between mass, velocity, current, and voltage. And here's the kicker. If you measure the voltage and the current using quantum electrical standards, specifically the Josephson effect for voltage and the quantum Hall effect for resistance, then those measurements are directly related to the Planck constant. The Josephson effect, discovered by Brian Josephson in 1962, when he was a 22-year-old graduate student at Cambridge, relates voltage to frequency through the ratio of Planck's constant to the electron charge. The quantum Hall effect, discovered by Klaus von Klitzing in 1980, relates resistance to the same fundamental constants. Both are quantum phenomena. They give you exact values, not approximate ones, determined by the fundamental constants of nature. So when you put it all together, the Kibble balance lets you determine mass in terms of the Planck constant. And if you can do that, if you can relate mass to the Planck constant with sufficient precision, then you can turn the logic around. Instead of measuring the Planck constant using a known mass, you can define the Planck constant as an exact number and use it to define mass. And that's exactly what happened. But the Kibble balance wasn't the only approach. There was a parallel effort, equally remarkable, that took a completely different path to the same goal. This was the Avogadro project, sometimes called the Silicon Sphere project. and it was primarily led by an international collaboration centered on the German National Metrology Institute, the Physikalisch-Technische Bundesanstalt, or PTB. The idea was to create a perfect sphere of silicon-28, a single crystal of ultra-pure silicon, enriched so that virtually all the atoms are silicon-28 rather than the naturally occurring mixture of silicon isotopes, and then determine, with extraordinary precision, how many atoms it contained. Why silicon? Because silicon crystals form a nearly perfect diamond cubic lattice, where the spacing between atoms is known with great precision from X-ray crystallography. If you can measure the diameter of a sphere to extreme accuracy, and extreme here means to within a fraction of a nanometer, a few atomic diameters, then you can calculate its volume. If you know the spacing between atoms in the crystal lattice, you can calculate how many atoms fit in that volume. And if you know the mass of a single silicon-28 atom, which you do, from mass spectrometry and other techniques, then you can calculate the mass of the sphere from first principles. You've essentially counted the atoms and calculated the mass from the count. The spheres themselves are objects of extraordinary beauty and precision. They're about 94 millimeters in diameter, a little smaller than a billiard ball, and they're the most perfectly round objects ever made by human beings. Their surfaces deviate from a perfect sphere by no more than about 50 nanometers, which is an almost inconceivable level of smoothness. If you scaled one up to the size of the Earth, the tallest mountain and the deepest ocean would be only about 2 to 3 meters. They're polished to such perfection that they look almost supernatural, like something from science fiction rather than a metrology lab. When you hold one, though they're far too valuable to casually handle, it feels uncanny. It's so perfectly smooth and round that your brain can't quite process it. There are no edges, no flat spots, nothing for your perception to latch onto. Scientists who work with them describe the experience as eerie, like holding a piece of geometry itself, rather than a physical object. The silicon used in these spheres, by the way, is some of the most expensive material ever produced. The enriched silicon-28 was made in Russia, at a centrifuge facility originally designed for enriching uranium. It was then shipped to Germany, where it was grown into a single crystal at the Leibniz Institute für Kristallzüchtung in Berlin, one of the very few places in the world capable of growing single crystals of this size and purity. The crystal was then machined and polished into its final spherical shape by the Australian Centre for Precision Optics. This is truly international science. Russian centrifuges, German crystal growth, Australian polishing, all in service of answering the question, how many atoms are in this sphere? Both approaches, the Kibble balance and the Avogadro project, converged on the same value of the Planck constant. And by the mid-2010s, the measurements had become precise enough to make the leap. On November 16, 2018, at the 26th General Conference on Weights and Measures in Versailles, in the same palace where the Treaty of Versailles had been signed, where the absolute monarchs of France had once held court, where the French Revolution had its political roots, delegates from 60 nations voted unanimously to redefine 4 of the 7 base units of the international system. There was a moment of genuine emotion in the room when the vote was called. Terry Quinn, the former director of the BIPIM who had championed the redefinition for decades, was in tears. Bill Phillips, a Nobel laureate who had worked on laser cooling of atoms, said it was the most exciting thing he'd seen in physics in years. For the metrologists in the audience, many of whom had spent their entire careers building toward this moment, it was the culmination of a dream. The vote took effect on May 20th, 2019, which was, fittingly, World Metrology Day. Here's what they did. They fixed the numerical values of 4 fundamental constants of nature, making them exact by definition. The Planck constant, h, was fixed at exactly 6.6260715 times 10 to the minus 34 joule seconds. This defined the kilogram. The elementary charge, E, the charge of a single proton, or the magnitude of the charge of a single electron, was fixed at exactly 1.602176634 times 10 to the minus 19 coulombs. This defined the ampere. The Boltzmann constant, K, was fixed at exactly 1.380649 times 10 to the minus 23 joules per Kelvin. This defined the Kelvin. The Avogadro constant, Na, was fixed at exactly 6.02214076 times 10 to the 23rd per mole. This defined the mole. And these joined two constants that had already been fixed, the speed of light, which had defined the meter since 1983, and the cesium transition frequency, which had defined the second since 1967. Think about what this means. Every base unit in the International System of Units is now defined by a fundamental constant of physics. The kilogram is no longer a piece of metal in a vault. It's a consequence of the Planck constant. The meter is a consequence of the speed of light. The second is a consequence of atomic physics. The Kelvin is a consequence of the Boltzmann constant. None of these definitions depend on any particular artifact, any particular material, any particular location. They depend on the laws of physics, which are, as far as we know, the same everywhere in the universe and at every point in time. This is, I think, one of the most beautiful intellectual achievements of modern science, and it barely made the news. The metrologists worked for decades, some of them for their entire careers, to make this happen. Brian Kibble himself didn't live to see it. He died in 2016, 2 years before the vote. The balance that bears his name. It was originally called the Watt balance, but was renamed in his honor after his death, was his life's work, and it changed the foundations of measurement forever. That platinum iridium cylinder is still sitting in its vault in Sèvres, by the way. It's a historical artifact now, not a definition. The kilogram has been set free. And here's something poetic about the whole thing. Remember how the original meter was supposed to be 1/10,000,000th of the distance from the pole to the equator? Méchain and Delambre spent 7 years measuring the Earth to make that definition real, and they got it slightly wrong, partly because of Méchain's hidden error, partly because the Earth isn't a perfect sphere, partly because their instruments, good as they were, had limits. The original meter was off by about 1/5 of a millimeter from the intended value. But it didn't matter, because once the platinum bar was made, the bar defined the meter, regardless of the Earth's actual dimensions. The definition detached from its origin. And now the meter is defined by the speed of light, which has nothing to do with the Earth at all. The definition has traveled from a king's arm to the Earth's meridian, to a platinum bar, to a wavelength of light, to a universal constant. Each step took the unit further from human arbitrariness and closer to something permanent, something cosmic. And that journey, that long, slow arc from the cubit to the Planck constant, is the story of measurement itself. It's the story of humanity saying, we want our numbers to mean something, not just locally, not just today, but everywhere and always. We want to anchor our descriptions of the world to the world itself, to the deepest structures of reality, so that what we say about a meter or a second or a kilogram isn't just a convention, but a fact about the universe. And now, with that story behind us, let's think about where measurement goes from here. Because the quest for precision doesn't stop. It can't. The better your measurements get, the more you discover, and the more you discover, the more precise your measurements need to be. It's a beautiful, self-reinforcing cycle that has been driving science forward for centuries. And right now, in laboratories around the world, People are pushing the boundaries of what can be measured in ways that would have seemed like magic to Delambre and Méchain, or Harrison, or even to Lord Kelvin. Let's start with distance, because the range of things we can now measure is genuinely staggering. On one end, there's the LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, which detects gravitational waves, ripples in space-time itself, caused by cataclysmic events, like the collision of black holes billions of light-years away. LIGO does this by measuring changes in the length of its 4-kilometer-long laser beams, and the changes it's looking for are incredibly, absurdly small. When a gravitational wave passes through the detector, it stretches one arm and compresses the other by a tiny, tiny amount. How tiny? About 1/1000th the diameter of a proton. That's about 10 to the minus 18 meters, a billionth of a meter. LIGO can measure that. Human beings built an instrument that can detect a change in length smaller than an atomic nucleus across a distance of 4 kilometers. That is, by almost any reasonable standard, the most precise measurement ever made. And they used it on September 14, 2015, to detect gravitational waves for the first time, ripples produced by two black holes spiraling into each other and merging, roughly 1.3 billion light-years away. The signal lasted about 0.2 of a second. The entire measurement, the distortion of space-time at Earth, caused by a collision that happened over 1 billion years ago, was encoded in a change in arm length of about 0.004 of the diameter of a proton. When the LIGO team announced the detection in February 2016, it confirmed a prediction Einstein had made in 1916 and opened an entirely new way of observing the universe. And it was, at its core, a measurement. An absurdly, almost impossibly precise measurement, but a measurement nonetheless. The same fundamental act, putting a number on something, that started with a pharaoh's cubit rod 5,000 years ago. On the other end of the scale, we're measuring distances across the observable universe. The James Webb Space Telescope, launched in 2021, can see galaxies so far away that their light has been traveling for over 13 billion years. The observable universe is about 93 billion light-years across. And yes, that number seems paradoxical for a universe that's only about 13.8 billion years old. But that's because space itself has been expanding while the light was traveling, stretching the distances. And we know these distances not from one measurement, but from a whole chain of measurements, a cosmic distance ladder, where each rung calibrates the next. You start with parallax, measuring the apparent shift of a nearby star against the background of more distant stars as the Earth orbits the Sun, and that works out to a few hundred light-years. Then you use certain types of variable stars, called Cepheids, whose intrinsic brightness is related to how fast they pulsate, as standard candles, to measure distances to nearby galaxies. Then you use Type 1a supernovae, which have a known peak brightness, to reach out to billions of light-years. Each step depends on the one before it, and any error at one rung propagates to all the rungs above it. The entire edifice of cosmic distance measurement is a chain of calibrations, and the precision of each link matters enormously. In fact, there's a famous ongoing debate in cosmology, the Hubble tension, that comes down to a measurement disagreement. Different methods of measuring the expansion rate of the universe give slightly different answers, and the discrepancy is large enough that it might be telling us something new about the physics of the cosmos, or it might be a systematic error somewhere in the calibration chain. We don't know yet. The resolution might reshape our understanding of dark energy, or it might come down to a subtle bias in how we calibrate one particular type of star. Either way, it's a reminder that at the frontier of science, measurement isn't just a tool, it's the battleground where new physics is discovered. And what about time? The best optical atomic clocks currently in development are sensitive enough to detect the difference in gravitational time dilation between 2 points, separated by a height of just 1 centimeter. Think about that. Einstein's general relativity says that time runs slightly faster at higher altitude, farther from the Earth's center, where gravity is a tiny bit weaker. And modern clocks can actually detect this difference over a height change of 1 centimeter. If you put one clock on the floor and another on a shelf 1 centimeter higher, and you ran them long enough, you could tell which one was higher based solely on which one ticked slightly faster. We're measuring the curvature of space-time across the span of a fingertip. These kinds of clocks aren't just laboratory curiosities. They have potential applications that are genuinely transformative. Geophysicists could use them for relativistic geodesy, measuring the Earth's gravitational field with such precision that you could detect underground density changes, like magma chambers or aquifers, from the surface. You could monitor sea level changes, ice sheet dynamics, and tectonic processes with unprecedented sensitivity. The clock becomes a gravitational sensor, and measurement becomes a window into the hidden structure of the Earth. But every measurement, no matter how precise, eventually runs into a limit, and the deepest limit of all comes from quantum mechanics. Werner Heisenberg showed in 1927 that there is a fundamental, irreducible uncertainty in certain pairs of physical quantities: position and momentum, energy and time. The more precisely you measure one, the less precisely you can know the other. This isn't a limitation of our instruments, it's a property of reality itself. You cannot, even in principle, know both the exact position and exact momentum of a particle at the same time. The universe simply doesn't have that information to give. Heisenberg's uncertainty principle sets the ultimate floor on measurement precision, and it's quantified by, you guessed it, the Planck constant. That same tiny number, h, that Max Planck introduced in 1900 to solve the black body radiation problem that Einstein used to explain the photoelectric effect, that governs the energy levels of atoms and the frequency of cesium clocks. It also determines the fundamental limit of how precisely we can know the world. The precision of our measurements has been steadily approaching this quantum floor, and in some experiments, we're already there. LIGO, for instance, operates so close to the quantum limit that it has to contend with quantum noise, random fluctuations of the vacuum itself, the zero-point energy of empty space, creating tiny jitters in the positions of its mirrors. And this is where, if you've been drifting in and out tonight, all the threads come together. Because the Planck constant isn't just important for defining the kilogram or for setting the quantum limit on measurement. It also appears in the natural system of units proposed by Max Planck himself back in 1899, the Planck units. These are units built from the most fundamental constants of nature: the speed of light, the gravitational constant, the Planck constant, and the Boltzmann constant. When you combine them in the right way, you get natural scales for length, time, mass, and temperature that don't depend on any human choices at all. The Planck length is about 1.6 times 10 to the minus 35 meters, roughly 100 trillionth of a trillionth the diameter of a proton. The Planck time is about 5.4 times 10 to the minus 44 seconds, the time it takes light to travel one Planck length. The Planck mass is about 22 micrograms, which is oddly large compared to subatomic particles. The Planck temperature is about 1.4 times 10 to the 32 kelvins, a temperature so hot that our current physics can't even describe it. These Planck units are thought to represent the scale at which our current theories of physics break down, where quantum mechanics and general relativity, the two pillars of modern physics, come into direct conflict and something new is needed. Below the Planck length, we don't know what space means. Below the Planck time, we don't know what time means. At the Planck temperature, we don't know what temperature means. These are the ultimate limits, not just of measurement, but of the concepts that measurement relies on. We literally don't have the physics to describe what happens at these scales. It's like asking what's north of the North Pole. The question feels meaningful, but the framework that gives it meaning has run out. Some physicists believe that space itself might be quantized at the Planck scale, that if you could zoom in far enough, the smooth spacetime described by general relativity would dissolve into something discrete, something granular, maybe something resembling a foamy, bubbling structure that only looks smooth from far away, the way a beach looks smooth from an airplane. Others disagree. We simply don't know yet. The measurement precision needed to probe the Planck scale is so far beyond what we can currently achieve that it may be centuries before we get there, if we ever do. And here's what's quietly beautiful about that: the Planck constant. This number that started as a mathematical trick to fix a problem with the glow of hot objects turns out to define the very boundary of the measurable universe. So where does that leave us? Let's zoom all the way out and see the whole arc of the story we've walked through tonight. 5,000 years ago, a pharaoh's builders measured the base of the Great Pyramid using a cubit rod calibrated against a master standard. They were anchoring their measurements to a physical object, a piece of granite. 3,000 years later, French revolutionaries measured the Earth's meridian to define the meter, anchoring their measurements to a feature of the planet. A century after that, scientists built platinum prototypes, anchoring measurements to carefully crafted artifacts. And then, step by step, over the course of the 20th and 21st centuries, metrologists unhooked each unit from its physical anchor and retied it to the constants of nature: the speed of light, the cesium transition frequency, the Planck constant, the elementary charge. Each transition moved the foundation from something local and contingent to something universal and permanent. That progression, from body to earth to artifact to atom to fundamental constant, is the deep arc of this story, and it's driven by a single impulse: the human need for reliability. We measure things because we want to be sure that the bridge will hold, that the medicine is the right dose, that the satellite is in the right orbit, that the clock on your phone matches the clock on the trading floor, matches the clock on the GPS satellite 20,000 kilometers above your head. And for that sureness to work, the measurements have to mean the same thing everywhere, to everyone, forever. That's what the whole enterprise has been building toward. And now, lying here in the dark, you're connected to all of it. The light from your phone, if it's still on, arrives in photons whose energy is quantified by the Planck constant, the same constant that now defines the kilogram. The Wi-Fi signal reaching your device oscillates at a frequency measured in hertz, a unit derived from the second, which is defined by the vibrations of cesium atoms. The dimensions of the room you're in can be expressed in meters, defined by the speed of light. The temperature of the air around you can be expressed in kelvins, defined by the Boltzmann constant. Every number that describes your physical world right now, every length, every mass, every temperature, every duration, is traceable through an unbroken chain of logic and experiment to the fundamental constants of the universe. That's not just impressive engineering. That's something deeper. It's a statement about the relationship between human beings and the physical world we live in. We started by holding up our forearms and calling that a measure. We ended by holding up the Planck constant and calling that a measure. And the fact that both work, that you can build pyramids with cubits and atomic clocks with fundamental constants, says something wonderful about the consistency of the universe and the ingenuity of the species trying to understand it. Measurement seems mundane. It seems boring, even. The kind of thing that somebody else worries about. But underneath that apparent boringness is one of the most profound things humans have ever done. We've figured out how to describe the universe in numbers that are reliable, consistent, and shared. We've built a language of precision that lets a scientist in Japan, and an engineer in Brazil, and a doctor in Nigeria, and a farmer in Canada all mean the same thing when they say a kilogram, a meter, a second. That's an extraordinary achievement. It didn't happen by accident. It took centuries of work by thousands of people, most of whom you've never heard of. The metrologists, the instrument makers, the committee members, the laboratory technicians who spent their careers comparing one platinum cylinder against another with microgram precision, year after year, because getting it right mattered. And it still matters. Right now, as you lie here, the clocks are ticking, the atoms are vibrating, the light is traveling at exactly 299,792,458 meters per second, and the Planck constant holds steady at 6.62607015 times 10 to the minus 34 joule seconds. These numbers are the quiet foundation of everything. They were here before we knew about them. They'll be here long after. And somewhere in a lab, right now, maybe at NIST in Boulder, Colorado, or at the PTB in Braunschweig, Germany, or at the National Physical Laboratory in Teddington, England, the very place where Brian Kibble built his balance, someone is measuring something a little more precisely than anyone has ever measured it before, pushing the boundary outward one more decimal place, because that's what we do. We measure, we refine, we try to see the world a little more clearly than we did yesterday. That's a good thought to carry into sleep. The world is precise, even when it feels chaotic. The numbers hold, even when everything else seems uncertain. And the quest to measure it all, from the pyramids to the Planck scale, is still going, still refining, still reaching for something a little more exact, a little more true. Let that settle. Let your breathing slow. And let the cesium atoms do their counting. 9 billion times a second. Perfectly, reliably, ticking away the moments as you drift off into the unmeasured, unmeasurable, deeply personal territory of sleep. The metrologists can measure almost everything now. The length of a proton, the age of the universe, the mass of an electron to 10 decimal places. But they can't measure this particular moment, in this particular room, with these particular thoughts, dissolving into dreams. Some things still belong entirely to you,